Good morning. I'd like to extend a warm welcome to all attendees. Thank you for tuning in to today's session of Cosmic Tales. Today, we'll be talking about the exciting field of gravitational astronomy. This area of research was made famous by the detection of gravitational waves by LIGO in 2015. Since then, gravitational waves have paved the way for a brand new frontier in astronomy. To talk more about this exciting new field, we have two eminent scientists with us. Our first speaker for today is Dr. Ajith Parameswaran. After completing his BSc and graduating with an MSc from Mahatma Gandhi University, he completed his PhD at the Max Planck Institute for Gravitational Physics. Today, he is a physicist at the International Center for Theoretical Sciences in Bangalore. His research spans many different aspects of gravitational wave astronomy. He has been a member of the LIGO scientific collaboration since 2004 and has been directly involved in the recent LIGO discovery of gravitational waves. He has received many accolades in his career, including the Gruber Cosmology Prize in 2016, the Special Breakthrough Prize in Fundamental Physics in 2016, and the Anna Sen Young Researcher Award in 2019. Our other esteemed speaker is Dr. Tarun Souradeep. Dr. Tarun Souradeep graduated from IIT Kanpur and pursued a PhD in gravitation and cosmology from IUCAA. He has built and led a cosmology subgroup on the cosmic microwave background studies. His contribution to science has received international recognition. He has been elected Fellow of the International Society on General Relativity and Gravitation in 2013 and is a co-recipient of the Special Breakthrough Prize in Fundamental Physics in 2016 and the Gruber Cosmology Prize in 2018 for the recent discovery of gravitational waves. It is our honor and privilege to have you as our speakers today. So without further ado, I'd like to hand over this session to our esteemed speakers. And after the session, we'll open the floor for a Q&A.
Good morning. And before I start, I would like to thank the organizer for this kind invitation. And today, Professor Souradeep and I will try to give you a flavor of this really emerging field of gravitational astronomy. And in the first talk, I will try to set the stage by giving you a brief introduction to gravitational waves and the astronomy using gravitational waves, and a summary of the most important results that came out of the observations of gravitational waves by LIGO and Virgo in the last 5-6 years. And Professor Souradeep will sort of talk about the future, especially that involves the Indian observatory LIGO India. So that's our rough plan. So I assume that most of you are already familiar with what gravitational waves are. However, I'll still give you a very quick intro to what gravitational waves. The existence of gravitational waves was predicted as part of the general theory of relativity, which is a theory proposed by Albert Einstein more than a century ago. And this is the most accurate theory of gravity that we have right now. So this theory describes gravity as a curvature of space and time. And any massive objects and as well as other forms of energy would produce a curvature in space-time. So both the curvature in space as well as in the flow of time, so to speak. And in Einstein's theory, space and time are not independent objects. They're part of a single object called space-time. And massive objects and other forms of energy would curve the space-time, which would have a number of very interesting consequences. And all of these effects have been verified by a large number of astronomical observations as well as laboratory tests in the last century. And the general theory of relativity has passed all the observational tests with flying colors so far. And the one very intriguing prediction that was met with a direct observational verification most recently is the existence of gravitational waves. And gravitational waves are basically freely propagating oscillations in space-time. And they are produced when massive objects move with an acceleration in the space-time, so that there is a change in the quadrupole moment. So here, there is a cartoon animation that shows two stars or two compact objects orbiting each other. And since these masses are moving around each other, producing with an acceleration, their motion produces basically changes in the space-time curvature. And these oscillations propagate outward at the speed of light. And depending on the mass and the separation on the frequencies involved of the sources, gravitational waves can be potentially produced over a whole range of frequencies. So there is a whole spectrum of gravitational radiation, just like there is a whole spectrum of electromagnetic radiation going from all the way up to radio, from radio up to all the way up to gamma rays. And if you were to sort of make a comparison, sort of analogous plot of the spectrum of gravitational waves, this is such a like a cartoon version. The left side shows the longest wavelengths of gravitational waves that could exist in the universe, which have wavelengths comparable to the observable universe. And the high frequency waves can be, again, arbitrarily small, but it depends on whether there are significant astrophysical sources that can produce gravitational waves of this kind of frequencies. So the highest sort of frequencies of gravitational waves that we know of exist in the universe is of the order of a few kilohertz. And so depending on this frequency range, there are, at high frequencies, there are more familiar astrophysical sources like the collapse of massive stars producing supernovae, or rapidly spinning neutron stars, or the in-spiral and the further coalescence of compact objects including black holes or neutron stars, etc. And indeed, and the frequency range that is probed by LIGO and Virgo and will be probed by LIGO India, etc., are in this sort of high frequency regime of gravitational wave astronomy, which is from about 10 hertz to a few kilohertz. So this is sort of the analogous of these sort of X-ray or gamma rays in the electromagnetic spectrum. But if you go to lower frequencies of, let's say, millihertz, then there is a proposed space-based observatory called LISA, which will observe gravitational waves from binaries of supermassive black holes that are of millions of solar masses that we know exist in centers of galaxies, including our own galaxy. And when such black holes come in pair with a binary system with another companion supermassive black hole, then such signals could be detected by LISA. Also, when there is a small compact object, like a small black hole or neutron star orbiting around a supermassive black hole, like the one in our galactic center, it produces, again, gravitational waves of frequencies of millihertz. This is called an extreme mass ratio in spiral. And even more massive black holes, supermassive black holes, which are of billions of solar masses, could produce gravitational waves at lower frequencies of the order of nanohertz to microhertz. And this range is being probed by what are called pulsar timing arrays. They look at make precise timing models of very large number of millisecond pulsars. And when gravitational waves pass through the Earth, then that could produce a change in the arrival times of a large number of pulses large number of pulses from large number of pulsars, which could be detected using a number of radio telescopes. Similarly, gravitational waves of very long wavelength can produce changes in the polarization content of the cosmic microwave background radiation. There are a large number of experiments that look for such changes in the polarization of the cosmic microwave background radiation, on which Professor Souradeep is an expert. So I want to drive home the point that there is a whole spectrum of gravitational waves, and we are only starting to probe a very narrow range of this whole spectrum of gravitational waves. And in the decades, more and more observatories would open up the full window of this gravitational wave spectrum. Even before the LIGO and Virgo observatories started making their detections, it's only in the last 6 years, we did have a pretty strong observational evidence, although indirect, of the existence of gravitational waves. And this came from the observations of radio pulsars, in particular, this remarkable system, which is codenamed PSR B1913 plus 16, or popularly known as Hulse-Taylor binary. This is a binary system of two neutron stars which orbit each other, and they have orbital frequencies of several hours, and they produce pretty strong gravitational waves, although we do not have any detectors that can observe the gravitational waves coming from such frequencies yet. But because the system loses energy and angular momentum into gravitational waves, these neutron stars would come closer and closer, and this would change the frequency, the orbital frequency of this binary pulsar system, which can be measured through radio observations. And this is the plot here shows the change in the periastron time of this binary system as a function of a year starting from early 70s. So this is a sort of radio observation that lasts for the last 3 decades. And these dots, black dots here, shows the actual measured changes in the periastron time. And the black line is not a fit to the data. It's a prediction from how this orbital frequency or orbital period would change. Because we can make a calculation because we know the masses of the system and this orbital eccentricity, and using general relativity's reading order calculation, we can predict how the orbit will change. And this observation agrees remarkably well with the prediction of Einstein's theory. So the change in the orbital period of the binary agrees with the prediction with like third significant digit. So it's an extremely precise astronomical observation, which verified the existence of gravitational waves for the last couple of decades. And what has been happening in the last decade in particular, a bit more, is an effort to detect gravitational waves directly passing through the Earth and using them as a probe of astronomy. And there are many ways of attempting this, and the method that met with the first rounds of success is using laser interferometer detectors. And they basically work on the understanding that gravitational waves are basically propagating tidal forces. So when gravitational waves propagate through the Earth, their tidal forces basically deform the geometry of space-time in a very characteristic manner. So the space gets stretched in one direction and compressed in the opposite direction, the orthonormal direction. And both these directions are perpendicular to the propagation direction of gravitational waves. So this is similar to, for example, how moon would introduce tides on the Earth, right? But the difference here is that these deformations are entirely transverse to the propagation direction. So the space gets stretched in one direction and compressed in the other direction. So if you have sort of free particles that are free to move, then basically they trace the moment, the change in the geometry of space-time. So for example, if you have a ring of freely falling particles, then this sort of circle of rings would get deformed into ellipses in one direction. So there extends in one direction and compresses in the other direction. And the next half cycle of the gravitational wave, the direction of deformation change. And this sort of deformation in space can be read off using laser interferometers. So it's a very familiar technique. So if you have, here's an example of an interferometer. There is a laser beam that is sort of that shines on a beam splitter, which splits the laser beam into 2 orthogonal directions, and there are 2 end mirrors that reflects the laser beams that brings them back, and this interference pattern can be read out. And initially, the interferometer can be locked in the sort of dark fringe so that the interference is destructive. But when a gravitational wave passes through it, then the space gets stretched in one direction and compressed in the other direction. So if the alignment is appropriate, then the path length in one direction gets longer than the path length in the orthogonal direction, which would make a change in the interference pattern, which can be read off. So it's a very standard technique, but the challenge is that the expected disturbances caused by typical astrophysical sources of gravitational waves is very, very small. So for example, the kind of first gravitational wave signal that we detected produced a strain, which is sort of the change in the arm length divided by the original arm of the interferometer, arm length of the interferometer, that is of the order of 10 to the minus 21. So this means that even if you have a kilometer scale interferometer, the change in the arm length that's produced by these astrophysical sources is of the order of 10 to the minus 18 meter, which, as you know, is like 1,000 times smaller than the typical atomic nucleus. So it's a very precise, so detecting gravitational waves would require very precise measurements. So one has to make these instruments extremely large and sensitive and hence complicated. And we will hear more about these, the details of these experimental efforts from Professor Souradeep's talk, especially in the context of LIGO India. So here are some aerial photographs of the LIGO observatories in the US. And these are two L-shaped interferometers, which have an arm length of 4 kilometers each on both directions. And the LIGO India will be very similar. So these detectors have been operating with their initial configurations for the last close to 20 years now. But about 6 years before, in 2015, they underwent a major upgrade, and a new set of detectors were placed in these vacuum chambers called advanced LIGO, which had a factor of few improved sensitivities as compared to their previous generation of detectors. And as soon as these detectors started operating, they detected the first gravitational wave signal. So here is a multimedia visualization of the first gravitational wave signal. And this lasts only for a fraction of a second, like 0.2 seconds or so. And you can see there are two detectors in LIGO Hanford in Washington State and LIGO Livingston in Louisiana. And you can see the time series of the gravitational wave signal detected by the two observatories. And in the background, it also shows a time frequency decomposition of the data. So you can see that the frequency increases as a function of time, and so does the amplitude of the signal. There's a very characteristic signal, which is called a chirping signal, which is similar to the chirping of birds. And these signals are produced by the in spiral of compact objects. So similar to this binary neutron sensitive I described, it's called the Hulse-Taylor binary. So as the compact objects orbit around each other, they lose energy into gravitational waves, they come closer. And because they come closer, the conservation of angular momentum requires them to rotate faster and faster. And basically, the frequency of gravitational waves is a tracer of the orbital frequency. So when the orbital frequency increases, the frequencies also of the gravitational waves also increase. So that's why it's causing this chirping signal. And eventually, these black holes merge, or these compact objects merge to form a single object, which is most of the time a black hole, which is very, very fastly spinning. And in fact, these LIGO Virgo observatories have detected some of the most highly spinning black holes that we have seen, with a very precise estimation of the spin of the black hole. And by looking at the frequency evolution of the signal, one can actually read out the parameters of the source that is producing the signal. And the details requires a lot of modeling, very accurate modeling of the expected signals by solving the Einstein's equations and constructing a large number of models of the expected signals corresponding to different set of astrophysical parameters, like the mass of the black holes. And such templates are compared against the data using a sophisticated technique called Bayesian inference. And then one can actually read out a posterior distribution of the parameters. So essentially, by comparing the data with theoretical models, one can extract the properties of the source that is producing the signal, such as their masses, the distance, etc. So by studying the signal, the scientists in the collaboration have estimated that this first signal was produced by the merger of two black holes, each weighing about 30 times the mass of the sun, slightly more, at a very, very distant galaxy, about a billion light years away, about 400 megaparsecs. So, and And of course, this discovery received wide international attention. And the founding members of the LIGO, Ray Weiss, Barry Barish, and Kip Thorne, were awarded the Nobel Prize in 2017 for decisive contributions to the LIGO detector and the observation of gravitational waves. In the last 6 years, LIGO and its sister observatory, Virgo in Europe, have observed over 90 such gravitational wave signals. So here's a zoo of the compact objects that LIGO and Virgo have discovered. The vertical axis here shows the mass of these compact objects in units of solar masses. The x-axis has no meaning. And if you can imagine, each binary coalescence involves 3 compact objects. You start with 2 compact objects, and they will merge to form a single and more massive compact object, which is most of the time a black hole. And you can see that like a cluster here. This is the first one. This shows the merger of 2 black holes, about 20 solar mass and about 40 solar mass, merging to form a more massive black hole of about 60 solar mass. And if you carefully look at these numbers, you see that the final remnant black hole's mass is smaller than the total mass of the initial black holes. That's because part of the mass energy of this binary system is radiated as gravitational waves. Something like a few percent of the total mass energy of the system is lost into gravitational waves, and the remnant mass has certain less mass as compared to the total mass of these binary objects. And all these blue dots here are such black holes that LIGO and Virgo observations have discovered. And if you compare them against the black holes discovered by X-ray observations in our own galaxy, which are these sort of dark pink or crimson color dots, you can see that the LIGO Virgo black holes are typically much more massive than the black hole discovered by X-ray observations from our own galaxy. So this was a bit of a surprise for most of the astronomers. Most of the astronomers were expecting that the LIGO Virgo black holes would be very similar to the black holes that X-ray observations have discovered in our own galaxy. And it turns out that the LIGO Virgo observations have uncovered like a new population of solar mass black holes. And there are reasons for why these could exist. But still, what these black holes are produce is not entirely clear. I'll discuss a little bit about this in the next slide. Similarly, LIGO and Virgo have observed some binary systems of 2 neutron stars. In particular, there is this very remarkable observation called GW 170817, which was discovered not only in gravitational waves, but also observed a large number of electromagnetic telescopes have observed their electromagnetic counterparts, the merger also. And I'll discuss a little bit about that in the next few slides. So here is a zoo of compact objects that LIGO and Virgo have discovered, and they have, in particular, the black holes have quite different characteristics as compared to the black holes discovered by LIGO and Virgo. It's very hard to summarize the entire science of these observations in a single talk. But I'll give you some really important bullet points. These are the first detections of merging binary black hole systems and black hole neutron star binaries, like a mixed binaries of 1 black hole and 1 neutron star. And as I said, these observations uncovered a new population of black holes, which are quite heavy, more than 30 times the mass of the sun. There is one signal that shows a potential evidence of an intermediate mass black hole, which is a very long sought after object by astronomers. And there is again one mystery object, which sort of lies in between what is called a mass gap between a neutron star and a black hole. So we have a large number of neutron stars discovered as pulsars, and the most massive of them has a mass of the order of 2 solar mass, a bit more than 2. And similarly, we also have a large number of black hole candidates discovered by X-ray observations, and the lightest of them has a mass of about 5 solar mass. So the astronomers have wondered why there is no object in between these sort of 2 solar mass and 5 solar mass. And this one particular object that LIGO and Virgo have discovered lies right in between this. So it could be either the heaviest neutron star ever observed or the lightest black hole ever observed. We do not know which of them is true. And these observations also enabled us to do some of the first tests of general relativity in a regime of extreme gravity and extreme velocities. So these black holes or neutron stars, before merging, must be moving speeds close to the speed of light, like half the speed of light. So you have this extremely massive and compact object moving with very large velocities colliding. And this is where we expect deviations from general relativity, if exist, would manifest most likely. And so far, all these observations were found to be consistent with the Einstein's prediction, but we still have to look for very, very minute deviations. And these observations also have uncovered new mysteries, as happens in any new branch of astronomy. So, for example, although we know that these black holes exist now in the universe, it is not entirely clear how nature produces these black holes, and in particular, binaries of these black holes. So these black holes could be remnants of stellar stellar collapses, or they could even be primordial black holes. There are some cosmologists who argue that some of these black holes could be primordial black holes, which were produced in the very early universe. And the precise mechanism in which these black hole binaries form is also under debate, whether they are produced by the evolution of binaries of massive stars, or these black holes are produced, black hole binaries are produced in some dense environments like stellar clusters through some dynamical interactions, etc. This is still under debate, and there is a very active area of research happening with many papers, very interesting papers coming every week. So I, especially for the students, I encourage you to look at a summary of these papers. There are accessible science summaries produced by the collaboration papers, which are available under this URL. And one particular observation that really stands out from this crowd of gravitational wave signals is the first observation of a binary neutron star in spiral. So here is a very beautiful track of the time frequency track of a gravitational wave signal detected on the 2017 August. And you can see this very characteristic chirping shape, very precise estimation of the masses. And this was found to be consistent with a binary neutron star signal. And it's just very exciting. But to make it even more exciting, a short gamma ray burst was discovered at the same time, coming from the same location of the source. So a large number of astronomical telescopes looked at this patch of the sky. They scanned the whole patch of the sky and identified an optical counterpart of this merger. And in the following days and months, this patch of the sky was scanned, or this particular transient was observed by a large number of telescopes, starting from radio all the way up to gamma rays. And all of these discovered various kinds of counterparts of this merger in different frequencies of electromagnetic radiation. This is one of the largest multi-messenger follow-up of an astronomical source happened ever. And this produced a large number of very interesting results. And it's also uncovered the potential of what is called a multi-messenger astronomy, where you look at a phenomenon or a source using multiple messengers of astronomy, like electromagnetic radiation, gravitational waves, and possibly neutrinos in the future. And just to give you a flavor of some of the science that came out of these observations, and again, which would make it more attractive for future observations of similar kinds. So, for example, these observations provide some very interesting hints on the nature of matter at extreme densities. For example, as neutron stars are compressed to very high densities, and the form of matter that exists at this extreme densities is not clear, because we cannot produce these conditions in laboratory experiments. And neutron star provides a very natural laboratory to test the models of the equation of state of dense nuclear matter at these extreme densities, because as they orbit around each other at close separations, due to the tidal forces of the companion, these neutron stars get deformed into some ellipsoid shapes. And the amount of deformation depends on the equation of state of nuclear matter, which will have an imprint on the gravitational signal. by studying the gravitational wave signal, one can actually put constraints on the nuclear equation of state. And this simultaneous observation of the gamma rays as well as gravitational waves sort of confirm the speculation that these short gamma ray bursts, which were observed in the last couple of decades regularly, were produced by the mergers of compact objects, in particular involving neutron stars. That was a first observational confirmation of this theoretical prediction. Again, the simultaneous observation of the gravitational waves as well as electromagnetic waves provided a first experimental verification that gravitational waves travel at the speed of light. This was again a prediction of Einstein's theory, and now we have an experimental verification. And now we know that gravitational waves travel with the speed of light within a measurement accuracy of 10 to the minus 15. So it's a very precise measurement. Again, a test of Einstein's theory. Some very exciting news for cosmologists is that these simultaneous observations of gravitational waves and electromagnetic waves provided us a very different way of measuring the cosmic expansion rate. So as you know, there is the universe is expanding, and to make it more strange, the universe's expansion is accelerating in recent cosmological epochs. So it's a big mystery what is causing this expansion. So one way of addressing the theoretical models of this cosmological expansion is to make more and more precise measurements, which have better statistical as well as systematic accuracy. And there are currently very powerful ways of measuring the cosmic expansion rate of the universe using things like supernovae, but and an independent way of doing it in the cosmic microwave background radiation. But the gravitational wave observations provide a completely different way of doing the same measurement, and it's very important in astronomy and physics to do different measurements to rule out possible systematic errors, etc. So currently, the measurements, the precision provided by these measurements is very poor. But in the next few years, we hope that the precision of these measurements would improve and can help cosmologists to understand some of the major puzzles that exist in cosmology now. I also want to stress that the gravitational wave astronomy has only begun. So far, we have observed of the order of 100 gravitational detections, but LIGO and Virgo have not yet achieved their design sensitivities. That would be happening in the next few years. And new detectors like Kagra in Japan, and more exciting for us, the LIGO India in India, will join this international network of gravitational wave detectors and will significantly improve the sensitivity as well as other abilities of this international network of gravitational wave detectors, like the ability for us to localize the sources in the sky. And confidently, we can see that in the next few years, we are expecting hundreds of gravitational wave signals, possibly thousands. And this is just by extrapolating the current detection rate of compact binary coalescence by taking into account the expected increase in the sensitivity. We also expect new kinds of phenomenon and sources, like a detection of a stochastic background of astrophysical sources, like the large number of compact binaries is almost guaranteed in the next 5 to 10 years. We also expect the detection of very new phenomena like gravitational lensing of gravitational waves and continuous gravitational waves from rotating neutron stars, potential detections of primordial black holes. If a galactic supernova happens in our own galaxy, then we will see signals from that, etc. And one could not rule out the possibility of detecting something very, very unknown, something very out of the box also, which has happened in the history of astronomy. So this is again how we are progressing in the front of this very high frequency astronomy of using ground-based detectors. But as I told you earlier, there is a whole spectrum of gravitational wave radiation, which is all waiting to be probed. There are phenomena that exist in all these different frequencies. So all these improvement in sensitivity as well as the bandwidth of observations is allowing us to probe new phenomena. And this is, you can make comparison with electromagnetic observations, because if you observe the universe in microwave, you get a picture that is very different from the picture of the universe that you observe in optical, right? All these phenomena are very, very rich and complex and mutually informing and exclusive. And similarly, by expanding both the sensitivity as well as sensitivity and the bandwidth of these detectors, we are hoping to tap into new and new phenomena in the universe. And there is an ongoing effort internationally to think of the next generation of ground-based detectors, which are, there is two major efforts happening. One in Europe called the Einstein telescope, and in US called the Cosmic Explorer, which would dramatically increase our horizon for observing sources. In particular, they would be observing practically all black hole binaries in the universe in the mass range of all the stellar mass black hole binaries in the universe. So going into really, really cosmological distances, enabling us to do some very precise observations and access to very new phenomena. So similarly, there is an ongoing effort to build a space-based detector called LISA, which is led by the European Space Agency. And this has a frequency sensitivity of the order of millihertz frequency bands. So the sources that LISA will see are very different from the sources that LIGO and its sister observatories are seeing. LISA will see binaries of supermassive black holes, extreme mass ratio in spirals, binaries of white dwarfs in our own galaxy, etc., and possibly signals from early universe produced by things like phase transitions, etc. So there's a whole set of interesting science waiting to be explored in this frequency range, and there's a very active area of research also. So let me stop here and summarize a little bit. So the recent observations of gravitational waves by LIGO and Virgo have really opened up a new branch of observational astronomy. And if you want to count the highlights, these are the first detections of binary black holes, black hole neutron star binaries. They provide the first tests of general relativity in the regime of extreme gravity, and they have uncovered new populations of black holes in the universe. We have the first multi-messenger observation of a binary neutron star merger. They have produced some very strong hints on the equation of state of nuclear matter. They have identified the engine of short gamma ray bursts. They provided an independent way of measuring the cosmic expansion rate, or the Hubble constant. And there are many interesting science coming up now. And as these detectors improve their sensitivity and new detectors join the network, there are hundreds to thousands of events are expected in the next few years. And at the same time, in the next couple of decades, there are new kinds of detectors are coming up, in particular in space and underground, etc. They would significantly increase the sensitivity as well as the bandwidth of gravitational observatories. They are really going through the multi-wavelength observations of gravitational waves. And so these are really beginning of a new branch of astronomy and a new window to the universe. So let me stop here, and let me take, Tarun will take up from here. Thank you.
Thank you, sir. Tarun, sir, can you continue?
Okay. So you'd have the question answer at the end?
So we were thinking that we will do the Q&A totally at the end.
Okay, that's excellent.
Okay,
so let me just begin. I'll just share the screen. Can you see the screen?
Yes, sir.
Yes, sir, it's great.
Okay, great. Okay, so let me also add my thanks to the organizers of Nakshatra for this invitation. I'm really glad that 13 student astronomy groups have got together to on this single platform. It's an excellent initiative, and I'm happy to be part of this with this talk. So you heard a amazingly beautiful talk by Ajith. He, sort of sketched the science promise of gravitational waves. Uh, so, this is an area for the young, and this is something that's probably going to last many of your lifetimes in terms of what is ahead. Okay, so let me begin, and I will talk largely on the Indian effort. So in India, we have been involved with gravitational wave astronomy or gravitational wave detection from about 1990s with two notable groups, one in Ayuka, led by Sanjeev Gururandar on data analysis techniques, making foundational contributions there, and another at Raman Research Institute by Professor Bala Iyer, who's currently at ICTS. And their group focused on the predicted, waveform of gravitational waves. It's important to note that the discoveries we have been possible because we know what to expect. But going forward with more sensitive detectors, probably we won't be limited to that. We will start seeing things which we don't expect. So let me talk about the future of gravitational waves. And in the context of India, the future does involve the advanced gravitational wave observatory that's coming up in India. It's called LIGO India. And so let me again, as Ajith has already covered, so I'll just quickly remind you that what we are looking for is a very, very tiny change in length. This separation of two mirrors kept 4 kilometers away, which is 10 to the minus 18. And this was the peak sensitivity, peak signal strength of one of our strongest sources, which happened to be the first one. And so you can see the challenge is enormous, and it's a technical challenge that had to be overcome over 4 decades of research. So what was the broad direction in which we were kind of pushing the technology? So in daily experience, you talk about sort of, I can't see okay, so megameters to about millimeter scales are things that we are, if you do an international travel or something, to, you look at a tiny thing on your desk. That's what we are used to in daily life. But of course, we know in physics, we deal with atomic scales, nuclear scales, which are 10 to the 9, 10 to the 15 meters, right? But suppose now you want to consider studying things happening at much smaller scales than that. So it's like breaching a frontier. And these tiny things, one of the best way to go, sorry. Yeah. So we needed to get to attometers kind of accuracy in, the ability to measure distances, to be able to detect gravitational waves, okay, which is, like any big discovery, I wanted to emphasize that technology plays a big, big role. The fact that technologically we could build an apparatus which had the right technology to allow us to measure displacements of this kind is what enabled this lovely new area of science, frontier science, gravitational waves and gravitational waves astronomy. So as again you saw before, these are massive sized detectors, 4 kilometers in length, and these are the two in US, and they are mammoth apparatuses. So you can see that here, you can see that the beam tube, if you go and stand at the center, goes to a very large distance. It's just 4 kilometers, talking about what will happen in the future. But even 4 kilometers is a huge distance, which I learned while searching for sites. And then you look at the vacuum chambers involved, and there's a man here to set the scale. And I'd like you to note these. These are all from existing detector at Hanford. And, so this is a mammoth apparatus is what I wanted to say. It's also an extremely precise apparatus. So the kind of elements that we use for the detections are absolutely unique. So what you see here are 2 test masses. These are the ones whose displacement you're trying to measure. And these are 40 kilograms each, 34 centimeter diameter in the advanced LIGO. But the amazing part is the surface specification. The surface finish is 100 times better than the best telescope optics that we have in the world, right? So these are numbers here. They have to absorb very little light because, otherwise they will heat and melt because of the laser light falling on them. And you can see what it takes to set up such mirrors. So it's almost like a operation theater kind of garb, and people sitting and setting up these delicate mirrors on the suspensions. The suspensions are unique too. So you have this 40 kilogram glass mirror actually hanging at the end of a glass fiber. Okay, and that is all to make sure that you don't create mechanical vibration noises, thermal noises in the mirror. So any object at finite room temperature, you have thermal motion in it. But what you do by this clever system is to isolate all those fluctuations and push them to a frequency far outside the frequencies of interest for LIGO. And that requires the mirrors to be absolutely pure, the coatings to be very compatible so as to not cause a problem with this kind of way of isolating the vibrational modes. And so these are quantified for people who are aware of a bit of physics, resonance phenomena. You have something called a Q factor. And Q factor is how narrow is your note, right? And so these mirrors vibrate only in a very narrow band of frequencies, and other frequencies it rapidly falls off. And the Q factor here is enormous, like 10 to the 8. And these stacks of things which the mirrors hang are essentially a cleverly designed set of isolators whose basic physics is very simple. Actually, for the passive part, it is actually a inverted pendulum. But this is what is used to do this seismic isolations by 12 orders of magnitude. So anywhere on the Earth, the ground has vibrations at the level of micrometers, and you need to attenuate them to this kind of factors to be able to have hopes of detecting 10 to minus 18 meters. Okay. Then you have to have a interferometer like none before. So if you know that, you see interference patterns, you can see them with ordinary light, you can see them with sodium light, but you know that the best ones come from laser light. If you have seen interference patterns with laser, you can see that, the interference pattern is much better defined with lasers. Why is that? Because lasers are fairly monochromatic. But the lasers that you have seen are monochromatic only in an approximation. They do have admixture of adjoining frequencies in a frequency band. The challenge for LIGO is to make that band as small as possible. so that the frequency or the spread in frequency delta f over f should be of the order of, say, 10 to the minus 6. And that is achieved in this lasers, which are again very unique things in the, and done in global kind of collaboration. So the ones used in LIGO were developed in Germany, but there were competing models in other countries, and this one out, and maybe there will be other kind of lasers will come. But essentially, they have to be extremely stable in intensity and frequency, as well as very narrow line width. So this is like as close as you can get to the textbook definition of lasers. Lasers, I'm sure many of you will rattle off the definition as a monochromatic source of light. Okay, but technically nothing is exactly one frequency. So there's a width, and that width has to be very narrow to allow this kind of detection. Okay, and here is a noise curve, which I'll talk about a bit later. But let me show you that these detectors can be improved even further. Advanced detector, this pink line, which we are hoping to get in few years, can be further enhanced by using clever quantum measurement techniques, right? And I should tell you that LIGO India, which I'll talk about in a few minutes, will start off with such arrangement. And this has extremely close ties with an emerging area that you must have heard of in India, which is quantum technology, right? There is a huge effort in India to grow quantum technology, and LIGO India will be using quantum technology on macroscopic objects, right? And that is something I would like to draw at the attention of all young people. That's an amazingly fascinating field of science and engineering that will come up. Okay, so let me get to LIGO India. Here's a architectural design. This is actually a 3D rendition of drawings, which are fairly final and ready to go. Here's the central station. You can see it's about 20 meters high, and the 4-kilometer arms going out. The terrain that you see is actual terrain data obtained from ISRO. And of course, some of these lawns and trees are a bit of imagination, but they may or may not be there as you go. But after monsoon, the land is as green as you see here. Okay, so this is something fascinating, and this is going to come up in India. It is coming up in India. I should correct myself. In Maharashtra, in a place close to Nanded city. So why did we embark on this? So I should tell you the first proposal of this was made in 2011, and the science case has not changed from then. What was the science case? We did not anticipate that we will come up in time for being part of the discovery of gravitational waves, but we did know that a detector in India would amazingly improve our ability to do astronomy. And why is that? So this is something that really was used as a thing to sell LIGO India to the government. And, so people at the very top have seen this plot. And this shows the uncertainty in the sky of the first event that happened, the discovery event. And you can see that's a huge banana-shaped region. And that would actually, encompass like the entire, Big Dipper, a few of those Big Dippers, kind of stellar configurations here, right? And so 250 full moons. But if LIGO India was operating then, this would have been this tiny region in the sky. We would have known where the source was to a very, very good accuracy. And that is what we need in astronomy. We need to know where are the signals coming from. Gravitational wave detectors by themselves are kind of blind, but a network of them actually allows you to pinpoint. It's just like 2 ears allow you to tell you which direction the sound is coming from. Similarly, multiple detectors across the globe allow you to do that. Okay, and this is just a reflection of that. And this was, of course, in 2015, 2016, maybe the previous picture, but this picture is about, and this is actually generated by Professor Ajith's group. His student Mukesh made it on my request. So these are recent discoveries of black hole neutron star mergers. And you see the current uncertainties plotted on the sky. You can see these red banana-shaped places. This is for one event, and this is for another. So you didn't know whether it was here, here, here on the sky. If LIGO India was there, it would have been uncertain only in this tiny strip. Okay. Similarly, here, this uncertainty on the left would shrink to this almost little patch that you hardly can see on the right, right? And people have gone ahead and done that. So if whatever you see in purple are uncertainties of detection without LIGO India, just Hanford and Livingston, and adding LIGO India. Here, LIGO India is labeled as A. That's because LIGO India is coming up in a town called Aundha. Okay, so it will be probably the Aundha detector of the network. Okay, and you can see that the purple one contours shrink to these small blue, tiny blue ones when you add LIGO India. And that's very important to keep in mind. So what is LIGO India? LIGO India is a joint effort. It's an India-US collaboration, and there's funding from NSF and in kind from NSF, and large part of the funding is coming from the government through the Department of Atomic Energy and Department of Science and Technology through what are called mega science initiatives. Okay. And the institutions involved from the LIGO side are the LIGO laboratories in Caltech and MIT. And in LIGO India, it's the Institute for Plasma Research, IUCA, RRCAT. IUCA is the Inter-University Center for Astronomy and Astrophysics. This is Institute for Plasma Research. This is Rajaramana Center for Advanced Technology. And this is a division of DAE which deals with construction. So these are the four lead organizations, but there are about 15 more institutes, people from 15 more institutes involved in the whole game. And that should be very, very clearly mentioned. And the proposed Indian commitment is construction and operation of an advanced LIGO observatory. And it involves setting up the entire infrastructure, then installing the detector, and of course the team that can operate such a detector, upgrade it, and propose new configurations in the future. The US commitment is in terms of is in kind. So the key hardware that I showed you, the mirrors, the laser, the suspension system, these are all actually international collaborative efforts, which LIGO happened to have an extra copy of due to historical reasons, and is going to ship it to India. They are actually ready for shipping there. So what are the goals? I mean, as I said, LIGO India will allow full exploitation of gravitational wave observations, because you can see that now you can point much better once LIGO India comes up. What is important for the country is the high-end frontier technology it involves. So it involves the high-tech capabilities in photonics, lasers, control systems, many, many ways. Another, of course, I told you about why India in terms of the geographical advantage. It gives you a huge baseline from US of about 12,000 kilometers. This is kind of as distant as you can get on Earth. And but there is also a big demographic advantage, and which is why I don't miss any chance to talk to students. India is one of the countries where such a field, which is going to flourish in the next couple of decades, can grow in human strength, in grow, and because we have excellent undergraduate systems, and we need challenges for the young people, and this is a challenge like no other. And this is why we are already providing a research opportunity for undergraduate and postgraduate students, and we will be ramping it up in the coming years. So just to repeat, LIGO India is not just astronomy project. Of course, gravitational wave astronomy is the key science goal. It actually touches astronomy here, theoretical physics, as Ajith pointed out, in terms of showing you that the gravitational waves are massless excitations, and that Einstein's theory is right. It, of course, gives you a new window into doing precision measurements and fundamental tests. And these are the technologies I mentioned: quantum metrology, lasers, optical sensors, controls, vacuum, and huge computing. So it shouldn't be understated that the computing challenge is unprecedented, at least in India. Nothing else competes with it in terms of the computing needs that it will have. Okay, besides, of course, the higher education outreach, and very importantly, the pride of having such a detector. So we scoured the country for about 5 years before we could find a site that was best suited for us. And this is from a detailed site selection report, which was filed in 2016 after we started looking for a site in 2011. And we actually followed up 39 sites, of which many of them with visits and seismic study. And finally homed on to this one, which you can see is on the red triangle here. And I think this might show it better. So we are right bang in the middle of the country. And why? Because we are in the middle of what is called the Deccan Plateau. And Deccan Plateau is known to be one single monolithic mass which came out of major volcanic activities, and is one of the seismically quietest regions in the world. Okay, and we homed in on that and found a good site. We looked at few sites. Many of the sites we saw were in that region, but this turned out to be the most suitable. Things have been happening at the site since 2016, 17. We have acquired the site completely. Now, if you go there, even before acquisition, you would have seen these posts marking where the various detector elements will be, the 4 kilometers. Then we did a lot of excavation tests, geotechnical tests. There were about 200 drillings happening all over the site to conduct this. So these are all massive efforts that are underway. At this time, these are fresh pictures of our site office building. So it's at the site, a building which is almost ready. It's amazing that it progressed steadily through the pandemic. There's a all-weather station, and of course, as is wise to do in India, so we fenced up the site as soon as we acquired it. We have also been moving on the vacuum infrastructure that has to come on the site. Massive vacuum chambers that you saw, and some of these have been already prototyped and fabricated at the industry in Bangalore. And so there were measurements done, and these are this is a chamber. So just you'll get a sense of the scale in the next picture. I'll leave out the technicalities. Here are people standing next to the thing. Once it moved all the way from Bangalore to Indore and was offloaded near our LIGO India offsite facility, which is now the national training facility for LIGO India. And you can see the excitement of sending such things. These are just 2 of them. We'll be sending 14 such shipments, and they'll be running across the country on these huge trucks, which take a week or so to make its way across the country. And these are, so what will come up after we have leveled the site and put a concrete base, is this vacuum infrastructure, which will be entirely constructed by Indian industries. And this is kind of the skeleton of the thing. It will all hidden under the, of course, shell, but this is what it will be. And inside the vacuum chamber, you will have this very intricate optics. Okay, this is only the central part of it, and then these two go out to the end stations on the left and on the right and top. But you can see this is a much simplified form of the optics, but this already tells you that things are complicated in terms of setting these up, and these require immense expertise in making sure that the suspended optics remain under control. And they're like thousands, hundred thousands of control channels that run in parallel to that. This is our offsite facility in and which is now called the National Training Facility at RRCAT, which is ready. And it, as you see, the prototype chambers that we have built have been shipped there to set up a place where people can train to work inside this. So these chambers are such that people get in and install optics and other things inside these chambers, right? And these are something that we have to get into. So let me now just give you an idea of what are the noises that we are fighting against. Okay, so what you see here is the black curve is the noise that you have in in the strain, which is delta L over L. Okay, remember we wanted to get to 10 to 21, but now this is what advanced LIGO will get to, but over this frequency band. So what prevents us from going to low frequencies? You can see this yellow trace here, which is seismic noise, which just shoots up like a wall around 10 to 20 hertz, right? And it's very difficult to have terrestrial observations going there. Okay, and then there are various other noises, seismic noises, coating noises, and all of these have to be fought. And this red trace is the quantum noise, right? And so let me now just show you what is the future. Now, of course, India will be part of the extension of the gravitational wave network of the current generation. But there are already plans afoot, which Ajith showed you as third generation plans to find or build apparatuses, design the apparatuses and build them, which do better. And various apparatuses that have been proposed take advantage of various things. And to do that, you should broadly know that these noise curves, how do they scale with the size of the detector? Right, and you can see that many of the noises actually scale down with the size of the detector, some strongly, some not so strongly. Okay, and there are various takes on this. So the first one is something that Ajith mentioned in his talk, which is the Cosmic Explorer. It's a study done at this point, and it has been very strongly endorsed by what are called the Astro-Decadal Survey in US. So it's a US proposal to have a 40-kilometer arm length detector. So you can see that it's like a LIGO, but scaled up by a factor of 10. Okay, and 20 kilometers, so 2 observatories, and it would probably come up sometime late 30s or early 40s, 2030s. But what it will promise to do is really go beyond what we can hope to go. So these are plots in the sky of distant black holes, merger events, and these are neutron star events. Now, why don't we have anything in this part? That's because the universe is too young to have black holes, so you don't even expect them. And but you can see with Cosmic Explorer, you would be seeing all the events, merger events that are happening in the universe. So it will not it will have the sensitivity to measure any cosmic merger event at any time in the past history of the universe. And it's amazing, it's mind-blowing. At this time, just to point to you, we are at this cyan curve, right? So in neutron stars, we are hardly reaching out to this. And in black holes, we just started probing it. But slowly at the end of, when a LIGO India comes up, we will be in this blue trace, where we will be seeing a sizable amount of the black hole population, but not so much of the neutron star population, right? And this is Cosmic Explorer. Next, I'll point you to something which is another alternative way of improving this reach. Remember, I told you about the seismic wall, but that is seismic noise on the surface of Earth. But as you go deeper down underground, your seismic noise decreases significantly, because seismic waves are largely surface waves. And so the Europeans have decided to go deep. They are going big also. So they go from 4 kilometers to 10 kilometers. But the entire system, which is now it's an equilateral triangle of 10 kilometers. So there are, independent interferometers here, but, in this triangular configuration of 10 kilometers. And you have to go 1 kilometer down to reduce the seismic noise significantly. And they would be able to see sources at lower frequencies and hence improve matters. And you saw the reach. ET reach is pretty much similar to CE for black holes, and a little less for neutron star binaries. So this is the Einstein telescope. These are all, you can find them, look for them on the web. They're very exciting possibilities in the future. So I think it's a very thrilling time. I mean, the reason I wanted to touch upon these is these are things that India will be definitely part of, because we are part of the game now. And possibly we might also think of such things coming up in late, in 2040s in India. Okay, and these are amazing technology and science to work on. Science, both experimental science as well as theoretical science. But I would emphasize the kind of range of technologies that are involved here. I can't think of anyone who cannot be involved with these efforts, with whatever background, right? There's always scope to fit into the scheme of things for these kind of massive efforts.
Sorry, I'm still not sure about that.
Okay, sorry. This was my Siri. Okay, and this is what Ajith pointed out is the space-borne antenna, LISA. This has been something I've been hearing since I was just started my PhD in 1992. And this is a configuration of spacecrafts which are following Earth, about 30 degrees behind Earth. And although it looks like a rigid body which is rotating around, these are 3 free spacecrafts. They are not attached to each other because they are separated by 2.5 million kilometers. And they are exchanging laser light, which is shown in this red. And interestingly, it's even a nice study in dynamics to see that these 3 satellites set off in the particular pattern that it is actually maintain this configuration indefinitely if the Earth's ellipticity of the orbit is 0, right? So it's a very beautiful set of things that have been done. And this itself is a huge effort that is opening up, because this is a approved proposal likely to be launched in 2035. And I just wanted to mention, Ajith has already shown this, that the noise curve allows you to make measurements at a very different frequency. We were talking about tens of hertz to 1000 hertz. Here it's millihertz range of frequencies that will open up for this. And just to mention that LISA had very stringent requirements, and hence there was a space mission called LISA Pathfinder, which was already launched to test whether we can do this. What was amazing is what was required of that mission it did about an order of magnitude better, or even more, almost a couple of orders of magnitude better than this. So this is a technology well in hand, which we hope will fly in 2035. So let me end with this. You've already heard about this. So we have opened one window to gravitational waves, which is in the milliseconds range. The other one, which will open up in 2030s, 2035, once LISA goes up, will be in the minutes to hours time period. And the pulsar timing array, the nanohertz range, decades, and these will see new, absolutely different views of gravitational waves in the universe. And something very dear to my heart is the gravitational waves from the beginning of the cosmos, like the origin of the cosmos, which we are supposed to be inscribed in the cosmic microwave background polarization. And depending on what strength the signal is, we are, maybe 5 to 10 years away from detecting it. Okay, so I'll stop here and I'll thank you for your attention.
Thank you, sir. We will move to the Q&A part now. So, Rajat, can you begin?
Yeah, sure. So there is a question on YouTube Live. Approximately how many years will it take for the observatory to get constructed? So I think the person is referring to the LIGO India project.
Okay, so LIGO India, it will take about 6 years from now. So once the major construction, so the real thing kicks off when we start the major construction of those 4-kilometer arms, leveling the ground, and that has not started, although there is already construction activity. So we are expecting to get going by 2026, but it all depends on how much the pandemic has affected things in terms of the industries and the places which will do it. But it is, the expected time is 2026.
So moving towards the Zoom questions. So there's a question by Bhushan. Why can't we reduce seismic noise on the surface of Earth? Why do we need to go deep?
Okay, so again, I think it refers to my talks. The seismic noise, seismic waves are surface waves. So when you have seismic disturbances or an earthquake, so the actually what propagates out and causes earthquakes are seismic disturbances on the ground. These waves actually cling to the top part of the earth. So if you go down, you would improve. In fact, even seismic vaults, for example, are kind of kept isolated by going a bit underground. But here you go a kilometer down to very significantly reduce the seismic noise. That's because of the physics. I mean, it's basically the vibrations on the earth are seismic waves from this thing.
And so one more question. From the gravitational wave signal, how do we judge the number of objects participating in the process which produces these signals?
I think
Has there
Ajith should
been-
take that. Yeah. Sorry.
Just-
Sorry, I didn't mean to interrupt. Yeah.
Have there been signals with more than 2 participating objects, for example, triple mergers?
Sorry, was it to me?
Yeah, Ajith, I think you're better.
Yeah, so in principle, there is, you can have systems involving 3 black holes, and they would merge hierarchically, etc. And people have, for example, numerically computed gravitational wave signals from such systems. And astronomers also have observed triples. But the problem is there is a stability problem. If all these triples, 3 objects are contributing their gravitational force similarly, then the system is not stable. Typically what happens is that there is a tight binary, which is in orbit with a very another object with a large separation. So you could still treat this binary as moving in some external gravitational field. So to summarize, they could exist, but in practice, most of the times, you can think of this as an effective binary.
Okay. Many of the localizations without LIGO India are elongated in shape. Why is this so? Why is the uncertainty in one direction larger than orthogonal direction?
Ajith, do you want to go forward with that?
Go for it.
Okay, so it's essentially, what we are using is very straightforward triangulation. So for example, with our 2 ears, I can see the direction in which the sound is coming from, but I cannot see, in the direction perpendicular to the baseline, which is the distance between the 2 ears. I wouldn't know where. I mean, we get away with it because, most of the sounds would come from somewhere in the same level of altitude, right? So it depends a lot, on triangulation. So if there are 2 of them, which is largely the 2 US detectors which are contributing to most of the sources, Virgo detector sensitivity is not as large. So then these things come out as a banana, right? Particularly the ones where we only looked at the Hanford Livingston versus Hanford Livingston and India, right? So essentially you should get a total circle on the sky. The reason you don't get it is because there's additional information in terms of the wave strength that you see in the 2 detectors relatively, and that tells you some more about which is the more likely patch. But what is called the degeneracy, the uncertainty is large, because in principle, if you just do a simple-minded triangulation with 2 observatories, you will only get a circle in the sky.
Question from Sitara. What is the fundamental difference in the kind of physics insights we get from optical electromagnetic data versus gravitational wave data?
I think Ajith can take that.
Sorry, can you repeat the question?
Okay. What is the fundamental difference in the kind of physics insights we get from optical data versus gravitational wave data?
Okay. Yeah. So typically the optical and most of the electromagnetic signals are produced by oscillations of like atomic transitions or oscillations of charges, etc. Right? They are incoherent and produced by surface in the surface of, for example, stars and objects, etc. But gravitational waves are produced by coherent oscillations of massive objects like a black hole, etc. So they are representative of the bulk properties of the system, while typically electromagnetic waves most of the time are produced by incoherent oscillations of the surface properties of the system. Like imagine, for example, a star itself, right? You see only the surface of the star from its optical light. But if now, for example, you have a supernova happening, and if you observe gravitational waves from a supernova or even neutrinos in supernova, what you have access, you're able to access the interior phenomenon of that supernova. So they're qualitatively very different.
Yeah. So Ajith, if I may add, I mean, if you give the example of the neutron star binary case, right?
Yeah.
Whatever we saw in the optical and other wavelengths happened well outside where the neutron stars merged and collided, right? So these were phenomena which were happening from the debris largely, and then the radio observations was the cocoon around it. So, electromagnetic phenomena is shrouded, whereas gravitational waves, simply put, actually, since gravitational waves are transparent largely to matter, they are come unimpeded from the center. So what you saw in the neutron star binary event in gravitational waves was exactly the masses merging in forming a single object at the center. And what you saw in electromagnetism is the rich phenomena that happened with nuclear matter that was spewed out during this collision. And various processes happened which we expected largely, but they were amazing to follow them up with different things and make sure that our understanding of this phenomena was correct. Okay.
A question from Neve. Why are binary neutron star collisions so much rarer than binary black hole collisions? Is there any reason for this, or is it just because they are weaker?
Yes, I can take the. Yes. So
Yes,
intrinsically, it turns out that binary neutron star collisions are more frequent than the binary black hole collisions in the universe. However, as you have suspected in your question itself, the gravitational waves from binary black holes are stronger than the gravitational waves from binary neutron stars, because binary black holes are typically more massive, and the gravitational wave amplitude is sort of proportional to the mass of, or some power of the mass of the system. So this means that your ability to detect binary black hole collisions in the universe is larger than the ability to detect binary neutron star collisions. We have a larger horizon distance for binary black holes. That's why our detected sample is dominated by binary black hole signals, even though the intrinsic merger rate of neutron stars is larger.
So going by that logic, white dwarf collisions will be even more rarer, right?
Well, I said the binary neutron star collisions would be more frequent. So the white dwarfs are even lighter than binary neutron stars, right? So, okay, I don't know about the rate of binary white dwarf collisions. Basically, it means we type 1a supernova rate. Tarun, do you know?
I'll show you this plot again. That would help. I'll just share my screen and show you that Cosmic Explorer plot. I think that would answer most of your. So you see here, as Ajith was pointing out, that at this point we are hardly seeing any of the neutron star events that are happening, right? Our distance that we are measuring to for neutron stars is not really far enough to reach out to all the events that are happening. So all the yellow events here are not covered at all. In fact, it will not be even covered with the advanced detector that we will have in the future. But whereas we have already gone way into the population of black holes. Okay, and that is because black holes are, I think the surprise is that the black hole events are as many as they are happening to be. Is that right, Ajith? Because in the early days, the expectation was that neutron star mergers is what might be the first detections. In fact, our horizon till recently was always measured, or you say how sensitive is a detector, you would give it in terms of how far you can see a neutron star event.
Right.
Nowadays, you have this other measure of a 30 solar mass, 30 solar mass, because these were all unexpected. I mean, so in some sense, the surprise part is already unfolding.
No
one expected these black holes to be there and in such numbers. But now, of course, we know they are there. And we are digging much further into that population than we are to the neutron star, because neutron stars are weaker. And also, but the white dwarf, the thing is, LISA will see them so much that it will be a nuisance. It will actually, be like a background noise in LISA, the white dwarf binaries. Isn't that true?
That's true. Yeah. So in fact, LISA would see them as binaries, not necessarily as mergers. They would be continuous waves. They'll be so widely, most of them would be so widely separated that we will not be able to see them spiraling and producing a merger and a type 1a supernova, etc. But we see a large number of binary white dwarfs in LISA. And you're right in that about the binary black holes and neutron stars. See, of course, before the LIGO detection, we had no clue on the rate of binary black holes. While we had some expectations that binary neutron stars should exist because we have seen them as radio pulsars. And in some sense, that model of binary neutron star coalescence had less uncertainty as compared to the models of binary black hole coalescence. But it is a surprise that binary black hole coalescence rates were sort of in the higher end of the predicted merger rates.
So there is a question on YouTube by Sri. Which is the widely accepted theory for the formation of binary black holes?
Tarun, do you?
Yeah,
so there are, and there is no widely accepted theory. There are many proposed theories. One is that these are produced by the evolution of binaries of massive stars. So we know that the binaries of massive stars exist. And we also know that these massive stars, some of the massive stars at the end of their lifetime would collapse into black holes. And it is natural to expect that you can form binaries of black holes by the evolution of the massive binary stars. But if you look at the details, there are many problems. One is that most binary stars that we know are extremely large separations. And if you form them binary black holes, even with the age of the universe, you cannot bring them close enough so that these black holes would merge within the life of the universe. So there has to be some mechanism by which you bring these stars sufficiently close so that they would become black holes, and then the gravitational sort of radiation reaction can take them through a merger. And one popular method is what is called a common envelope evolution. So, and there is, but we understand the physics of the common envelope evolution not very much. So there are a lot of uncertainties in this. So that's one model. It's called isolated binary evolution. The second is called dynamical formation. And there are different sort of versions of this. And the general story is that if you have a dense environment like a stellar cluster where the typical number density of stars is much larger than that in the galactic disk, and many of the stars would, at the end of their lifetime, would collapse into black holes or neutron stars. And in general, and this massive object would sink to the center of the system so that there is a larger number density there. And there are various interactions, some multi-body interactions through which binary systems can form and get tightened. They can get closer and closer and merge. So these are the two sort of main models of this. And there are some other recent models proposed. One is called a chemically homogeneous evolution, etc. There are also some sort of more speculative models that some of these could be primordial black holes, and they can get closer in the galactic disks, etc. So we still do not know which of them is the most dominant formation channels.
So there are a lot of questions on the chat. Question by Lochan Dayani. When the laser enters the gravitational field of black hole, does the speed of laser slow down for us as the time slows down? If yes, does this affect the observation?
Yeah, so what we can measure very accurately is how the frequency of the laser shifts to lower frequencies. And this is called the gravitational redshift. And this has been measured very, very accurately and been established. Speed is a tricky concept. There is something called Shapiro delay, and you can think of this. Essentially, what we are seeing in the gravitational field, a signal will take a longer time to reach us. And you can interpret this in two different ways. One is that the speed of light speed of light is slowed down, or you can say that there is a larger distance to travel because of the curved path. But the observational effects are things like gravitational redshift and like Shapiro delay. So there is a longer delay for a signal to reach us. And this has been measured because in the case of binary pulsar system, you have two sort of distinct regimes. If you have a pulsar orbiting in a binary, and sometimes you can directly see the pulses without the interference of the second object. And sometimes if you have an edge-on system, the companion would come directly in front of the pulsar and us, which means that the signal has to go through the curved path, curved geometry of the space around the companion, and it will take a longer time. So this has been very precisely measured, and this is called the Shapiro delay. Tarun, would you like to add anything?
No, I think that was an excellent. I mean, only thing is, I'm not sure whether the question came with some understanding that the laser light never goes close to. You said something about a black hole warping the laser light, but the laser light is only on Earth, right? So the black hole merger happened many billion years ago in, billions of light years away. So, so certainly this laser light has no bearing on the black holes, but it does get affected by the gravitational waves shed by the black holes, which were merging. So that's in case that was
You have two
confused.
contacts named Martin. Which?
I'm sorry. Yeah. Okay.
So a question by Drishti. Is it only possible to obtain gravitational waves from astronomically massive objects? Can we, for example, get gravitational waves from atomic phenomena?
Ajith,
You can go ahead.
Okay, I mean, it depends on, see, any two objects which have mass and are gravitationally interacting in a way where the quadrupole changes would create gravitational waves. On the other hand, you should realize that the strength is extremely small. So the reason we are limited to astronomical black holes is because those at least have measurable effects, right? So if someone is, dancing on a skating rink or something, you are generating gravitational waves as long as you change the quadruple of your mass distribution. It depends on how big is that effect, right? And so even for stellar sized objects, you saw that it's a very tiny effect. In fact, so much so that Einstein, in his paper where he predicted gravitational waves, essentially said these are of academic interest or something like that. It was written in German, so I don't know exactly what he said, but he did not anticipate that someday we will do astronomy with gravitational waves of astronomical objects. So I think that is, the answer, but Ajith, if you wanted to add something.
No, I think that's perfect.
So a question by Sagar. Gravitational waves are ripples in space-time, and the presence of massive objects, say black holes, will curve the space-time greatly. So what will happen if a gravitational wave passes through a black hole? What will happen to the trajectory that is the path of the gravitational wave?
Ajith, you should, because you talked about lensing. So
yeah, so the effect of the change of the path of gravitational waves is exactly equal to that of the light. So for example, if a gravitational wave fall into a black hole, it would just absorb it. And in fact, the black hole can get slightly massive because of the energy of the gravitational wave. But this is a very, very pure theoretical sort of situation. But there are practical situations where we can actually see the effect of a black hole on a gravitational wave, which is called the gravitational lensing. And we do observe the effect of gravitational lensing on light so far. So basically, even outside the even horizon of the black hole, the gravitational effects exist. The space-time curvature exists. And because light travels through the curved space of this black hole or any other object, in fact, the light would bend. And in some extreme situations, then this bending can produce multiple images, etc. And it's a very regular observation in electromagnetic observation now, this gravitational lensing, it's called strong lensing, etc. And it turns out that gravitational waves will also be lensed exactly in the same way, but we have not yet observed it. And there are good reasons to believe that in the next few years, we will be making the first observation of the lensing of gravitational waves.
So that is an interesting topic for the coming few years.
Yeah.
A question by Behra Mitra. With so many opportunities opening up in gravitational wave research in India, if we want to work on the gravitational wave research in the coming years, what topics in physics or maths would you recommend to get a really good grasp of? So,
So that's largely depends on what kind of work you want to get into. But as I said, almost every version of physics that you can think of and engineering that you can think of, I may be able to match it to some aspect of the LIGO science. But you have to train as a physicist or as an engineer interested in pursuing physics after your engineering, pursuing physics aims, because many of the miraculous things that we have there are built by essentially engineers who have extremely good mechanical or electrical, electronics. Of course, also data science or computing. The kind of challenges we both did not touch upon that, because given all the challenges, that probably looks the most easily in hand. But those are also immense. The kind of things that are already going on to analyze the data, the machine learning. So essentially, it's a broad spectrum of people who may be able to join the efforts. And that is the excitement of having such mega science projects, because it can kind of accommodate people with very, very different skills. But if you want a very specific answer to getting into the kind of thing Ajith does, is absolutely you should go for physics. And of course, that physics involves knowing substantial amount of maths, and or engineering, where also at the cutting edge you require the same. And at some level I find these boundaries blur. There are physicists who essentially work as well as an engineer would do, and engineers who are slowly becoming very good physicists, particularly in quantum technology, for example. The merger is kind of seamless.
So question by Neev Shah. How do we know which polarization of the gravitational waves do we measure? Does it depend on the sky location and inclination of the binary?
The short answer is yes, but Ajith can give a simple answer. That will be good.
Right. So the case of binary is the measurement, the polarization is secular, and so the waveforms of the two polarization are very similar, except for a phase shift of pi by 2. Using a single detector or even a small number of detector, you cannot disentangle the polarization, because each detector measures only a linear combination of the two polarizations. And it turns out that the two LIGO detectors are very nearly aligned, so that they basically measure the same combination of the two polarizations. And the Virgo detectors helped a little bit, but here is where LIGO India could make a big impact. LIGO India being at a different part of the world and different orientation, pointing in a different direction of the sky. It is actually measuring a very different linear combination of the two polarizations. So one could actually extract within the limitations of noise, etc., the two polarization states separately in software by doing appropriate data analysis. So currently our ability to do that is limited.
Question by Dhruv Patel. There is some recent talk about setting up gravitational wave observatory on the moon. Like I also heard, there was a recent conference in Italy. So what advantage will it provide if suppose this thing actually happens? Because obviously setting up such a complex instrumentation on moon will be very difficult.
Tarun, do you want to take that?
Okay, I mean, I did attend the meeting, but I must say that at this point, it's a very nascent idea. It's not as if we are going to set up a LIGO on the moon, right? It's a slightly different way of measuring it, but there are challenges. So, for example, they have, although, so the main reason for going to the moon possibly are twofold. One is the seismic noise is, I think, a couple of orders of magnitude smaller than on Earth. or maybe more. I have to look back on the slides.
Yeah.
But there are moonquakes and things to worry about. So there are experts. I mean, I was amazed how many people spend their lives studying moonquakes, and there were experts talking about that. Other thing I vaguely remember is that, there's in the deep shadows of the crater shadow, the temperature is quite stable and also pretty low. And that may help with the kind of technology that you can deploy there. But I'm not too sure about how exactly that helps. But I'm sure in the coming years, we'll hear more about it. There are many, many science efforts which are seeking to go to the moon. And gravitational waves is certainly one of them. I'm sorry, I'm not as well informed as I should be on this, but it is certainly exciting.
Yeah,
And it's not something that you can dismiss.
It's a
It may
neat
well
idea,
happen.
and I want to add that even using the global seismometers network, using the ring, the Earth as a ring that would as a bell that would ring when the gravitational waves would pass. People have put upper limits on the stochastic gravitational wave background at certain frequencies. So it is a neat idea, and but as Tarun said, in terms of the actual sensitivity and other aspects of practicability, I don't know where it stands. But it's a very new idea, and it seems very interesting.
So, question by Saurav. In LISA, we can achieve greater length of interferometer arm. How will the sensitivity of our observation will be affected, as it is a more controlled system? What kind of noise can we expect to be present in LISA?
Okay. So LISA, the noise budget is very different. Of course, you're away from the Earth, and so there's no seismic wall, and that's why you are able to go to millihertz, and that's also because of this scale of the apparatus, 2.5 million kilometers. And so there are amazing challenges. Actually, when I told you that the configuration remains the same, it's only for if the Earth's orbit around the sun was not eccentric, it was circular. Okay, but it has a small eccentricity, and that causes shifts. So you have to keep control on the spacecraft so that they don't really wander around and they stay in that configuration. Then you have to exchange laser between spacecrafts which are 2.5 million kilometers away. So it's not as if the laser goes from one spacecraft and bounces off a mirror and comes back. That's just not possible. Okay, so what you get from the laser at that other end is almost picowatts of power. So you have to be able to detect it. Then you have to be able to sync it with a local clock on clock on the other one and send back a signal to the other two spacecrafts. And these are things that are being worked out, have been worked out to a large extent, are being worked out to improve further. There are challenges, immense challenges, but they're of a different kind. One of the challenges which LISA Pathfinder was launched for is to make sure that in a moving spacecraft, you can have something like the mirrors that we hang in LIGO, which are, for all practical purposes, in the plane of perpendicular to the hanging, are free masses, or at least that's what is required. So a free floating body inside a spacecraft which is moving around the sun is something that LISA Pathfinder showed was possible to the accuracy that is required to make LISA happen. And that was very amazing. So there are challenges, but we are going to overcome them, and LISA is definitely going to happen soon.
So I do have some questions regarding this LISA. So the time measurement will also be included, like precise time measurements to keep the three of them in sync, like GPS. Is it so? Like how GPS functions?
Ajit, do you have better information on that? I mean, I'm sure they must be carrying
Time
some
standards
clock.
again is using a laser, right? You have a local laser. That is the thing. I don't know exactly how that, but I think it's more precise than a GPS. If you want to do.
Okay.
No, it's not GPS, but so you don't carry a clock, but yeah, as you said, that one of the spacecraft becomes the reference. The laser in one of them becomes a reference for the times between the three lasers. Again, I'm not as familiar with Lisa.
So question by Nishkal Rao. Since gravitational waves also stretch compressed wavelength of light, red, blue shifts, hence light cannot be used as a length scale to measure the change of lengths of the interferometer arms. Is this paradoxical? How is it resolved?
So there's a very interesting history. So there was a I think, the answer, I don't know if Ajit has a very simple, quick answer, but it has to do with basically the time delay that is happening. But there's a very nice, accessible article written by Peter Solson many decades ago. And if you email me, I will send you the reference. That has, to my mind, one of the best explanations for what we are measuring with gravitational waves. But the question you asked is something that everyone thinks of in terms of the wavelength stretching and then the same number of wave numbers fitting between the two mirrors. So how does it make a difference? That's not what we are measuring. It's basically the number of the time delay accumulated over the number of bounces that we are measuring. Ajit, do you have a better thing? Or
No,
he talked about the gravitation redshift. So I don't know whether that's the easier way to.
I think what we are measuring is the time, the round trip time. As you rightly said, the Peter Solson's article on that. It's not New Journal of Physics. What is it called? That science education.
American Journal of Physics.
American Journal of Physics. Yeah. Yeah.
Yeah, I think someone should write a nice article on this. I keep referring to that.
So related question by Kaustubh. Why is there a discrepancy between black hole and neutron star with respect to the redshift to which we can detect signals with the same detector technology, referring to the Cosmic Explorer plot?
So it has to do with the strength of the signal, right? Intrinsically.
Okay.
So neutron stars cannot be more massive than 2 solar masses, right? Each.
So what are the
right, Ajit? I mean, you should correct me.
Correct.
Yeah.
Okay, so there is one last question. What are the probable new windows for gravitational wave research?
Ajit, go forward.
This is, I think, two open questions. I'll think of a few that I can answer, and then Tarun can also take up. See, there are different new ideas coming up. Now there are a lot of people who have very different expertise historically, have been interested in this field. New ideas are pouring in all directions. So, for example, the kind of idea that people are coming with for detection, new technologies for detection of gravitational waves, like, for example, using the seismometers on moon as a way of detecting gravitational waves is one thing. So there are, like, people have used, like, the proposed ways of using astrometry, like in Gaia and so on, are possible ways of detecting gravitational waves. There are numerous sort of tabletop, not numerous, but there are a few very interesting tabletop experiments proposed. So these are all new ideas, and some of them might actually lead to some very, very viable techniques in the future. That's sort of one thing. In the traditional sort of gravitation, and there is also established new pathways for building new detectors, like the third generation ground-based detectors and the space-based detectors like LISA, etc. Each of them have very different challenges, and not all of them are solved. And these are active areas of research. And even within the sort of LIGO Virgo type science, these observations have uncovered new mysteries, and people are trying to solve them. For example, the way nature makes these heavy black holes and binaries of heavy black holes, it's not solved. And also using these observations people try to solve existing questions like the expansion rate of the universe, dense nuclear matter, etc. And there are possible new phenomena that people are looking for, like the lensing of gravitational waves. And I am sort of personally interested in that. And these are all like new tools. And again, just like the gravitational lensing of light has become a powerful tool for astronomy, it is not impossible that the lensing of gravitational waves also would provide a useful tool. So these are all things that I can think of. Now, Tarun, you can add.
I can point to other exotic phenomena which we would definitely discover something or the other. Okay, so exotic phenomena like we do expect cosmic strings in various models of high energy physics, and cosmic strings tend to radiate, and there could be signals of that. It's a big question in general relativity about existence of naked singularities, and if we are wrong about that and there is something like that, people have talked about. So these are very exotic possibilities that might open up. But in terms of what is really, more or less in line with what we're doing, itself will keep us very busy. And, so if there's a surprise, of course, if the black holes turn out to be primordial, that itself is a big thing for cosmology, right? If you're saying that these primordial black holes are of cosmic origin. So we don't really know what are the extra windows that might open up, but I think the community has its hands full with what's happening right now. And, so that I think is one thing. And I think there was a question about theoretical methods for gravity wave measurements other than lasers. So, I mean, there could be, I think there's atom interferometry. I mean, I'm not saying that it doesn't use lasers, but not using the laser as the probe. Again, there are many other efforts that, Ajith talked about, which are tabletop, looking at oscillations of very small crystals and things like that. And these were efforts even pursued many years back, like Braginsky's group and, in Russia. It so happens that we don't expect gravitational waves so much at, frequencies of tens of kilohertz. I mean, but if it happens, it would be a surprise. So we should always look for them. Okay, this is something that Ajith can answer. When is O4 expected to start?
Yeah, so the current expectation is next August, 22 August. Oh, yeah.
Yeah. No, I mean, there could be some delays, but, because again, the pandemic has hit both the countries, and, so there may be some, but I think, yeah, August is what I also would say.
Yeah, there could be some delays also. I think, yeah, you're right. You say late next year is probably the safest.
Yeah, no. So I mean, so let me sort of explain how important it is for a community to think through when to switch on a gravity wave detector, right? So there's upgrades that you do when the detector is off, and the question is, how many upgrades do you do before switching it back on? So the delay you are incurring in switching it back on, you're missing sources. But of course, not adding an upgrade which will improve the sensitivity, you're missing sources. And it's a trade-off. At all points, it will be a trade-off. And so while it's August, I won't be surprised if there are further revisions to the starting date based on what upgrades you want to do. And just maybe this is probably at the end of the question answer. So there's a story which I think Ajith also knows about the first discovery. So one of the Nobel laureates is the person who built the detector, and so he was very unhappy with the state of the detector when they were switched on for the engineering run, because there was some radio frequency noise which they had not bothered to pin down. Okay. Nevertheless, the labs decided, based on whatever assessment, to switch it on. And if they had not switched it on, we would have missed one of the strongest signals that we have done. I mean, I think it came up in the engineering run within a day or so, or two. So, I mean, these are all, decisions you take in life, and in retrospect, of course, they look very smart, and but so it so happens. So similar things keep happening, right? There's a bunch of people who would keep saying, let's make the upgrades and delay the start of O4, and where the whole bunch of people who would be saying, we are missing sources, So yeah, it's always fun to listen on to all this. What's the time now? Oh my God. Okay.
I think we can close now, sir, because it's been pretty late, and
Yeah.
I think we can move to vote of thanks. So, Srirang.
Yes, thank you. So I'd like to cap off this extraordinary session by thanking our brilliant speakers for this mesmerizing and informative session. According to an old Japanese proverb, a day with a great teacher is better than 1,000 days of study. And we are blessed to have learned from not one, but two great teachers today. I'd also like to thank all of the attendees for making this session a lively and interactive one. And last but not least, I'd like to thank all of the volunteers who made this session possible. And with that, I'd like to conclude this session of Cosmic Tales. Thank you very much.
Thank you.
Thank you, Professor Tarun, Souradeep, and Professor Ajith. It was an honor.